Well, hello friends. Welcome back to the JavaScript bytecode series. After the last episode, I decided to upload and release all 7 episodes that I had recorded so far, and I got a lot of great feedback. People seem to really like the bundle of episodes coming out all at once. So it's definitely something I will try again in the future. But now that I've done this and also released the code, a bunch of other people have joined in on hacking on this, so it's not really feasible for me to do a bunch of episodes offline like that on this particular part of the code base. So it's been a pretty hectic couple of days since I published because a lot of people have worked on it, and we've seen some pretty awesome changes. And super thanks to everybody who has been helping out on the Bytecode VM. And let's talk about some of the changes, I guess, before we get into some hacking. So one of the big changes is that we now have an accumulator register. So if we make a test program here and we run that, then we see now that we previously had like multiple operands to many instructions. Like add would take like a source and a destination, and actually 2 sources and a destination. And now instead, what we do is most of these instructions operate on the accumulator register implicitly. So what we do here in this program now is that we load the immediate 1 into the accumulator, and then we store the accumulator into register 1. Then we load the immediate 2 into the accumulator and add the accumulator with whatever is in register 1. And that is how the result is produced. And this creates a much more compact bytecode, and I really quite like it. It simplifies a lot of things, and thank you, Matt, who implemented this. I think he said he got the idea from V8, which uses an accumulator architecture, and I thought this seems like a really nice architecture, so let's roll with it. And then another major change is that we now generate basic blocks instead of just one big block per function. So if I write a simple program that just loops a little bit like this, right? Then previously we would just generate one big hunk of bytecode for this. But now instead, what we do is we generate basic blocks. So we have 4 basic blocks here. So the first one is just the entry point and assigning 0 to I. And then here we start to do the while loop. And the while loop actually has a separate basic block for the test, so that it makes it much easier to express things and to also later on perform analysis on the bytecode. And I know a bunch of people have commented and suggested like, hey, why don't you do basic blocks? And Ali went and just implemented them last night, and I merged it this morning. So this is new. And I think it's going to be great to have that and help us move forward on improving the bytecode VM. And then these are the 2 major architectural changes, I would say. And then a bunch of people have helped out just adding code generation for various AST nodes and fixing little bugs here and there. And so we've been moving along very nicely. And today I thought we would do something pretty lightweight and just implement update expressions, which are prefix and postfix increment and decrement. So like plus plus I plus plus, minus minus I, and I minus minus. And yeah, so let's do those. Let's make a little test. So we start at I at like that. And then we will log plus plus, or we start with logging I, actually. Plus plus I, and then we can log I plus plus. And then we log I at the end. Yeah, something like that. And of course, we are missing generate bytecode in update expression. So that's fine. If we run this with the ASD interpreter, then it produces this output. Let's just triple verify with V8 here that it's fine. And why not also with, or I thought we could do it with JSC, but I think JSC actually uses print instead of console log. Is that what they do? I don't know. Sometimes I wonder if we should have a test mode that just exports functions that are similar to what other REPLs do, just for compatibility. But anyway, let's get into implementing this. So the update expression is it's the ASD node for all of these things, so let's take a look at one of them. So we have update expression right here. And the way that we express it in the ASD dump, I guess, is that we put the ++ on the side of the identifier, depending on if it's prefix or postfix. That's kind of cute. But if you look at the update expression ASD node class that we have, it has an update op, which is increment or decrement. And then it has an argument, which is the expression that we are incrementing or decrementing. And then prefixed tells us if it's a prefix or postfix. So that's it. So I think we can just go ahead and add a generate bytecode overload to this thing and then write some code. So update expression generate bytecode. Okay, so what do we want to do here? We want to, I think the first thing we're going to do is we're going to check, because update expression can be used with an identifier. If you're doing like ++I, then you're incrementing a variable, but you can also do like o.foo++, and then you're actually incrementing the property foo on the object o, which that's a little bit different. So let's not worry about that right now. And instead, let's just say like if is identifier argument. Yeah, so we'll do the identifier case and we'll leave the member expression case as a to-do. And then I guess we want to load the argument into the accumulator. So let's see, identifier. Let me just static cast this thing actually. Okay. So we want to load the bytecode op. You want to get the variable, right? So get variable now simply takes a name of a variable and it implicitly puts that into the accumulator register. So let's start by doing that. And then we can, let's see, update. I guess we need some other type of expression at this point. So we need to either increment or decrement. We could do that with like add 1, subtract 1, but that, I feel like incrementing and decrementing are such common operations that we can also just add opcodes for them. So I think let's do that. Let's do that. So increment, decrement, let's say, and then how will they look like? class increment. So they will, I think they will just increment and decrement the accumulator. Like that's actually really straightforward. So then they don't need any operands whatsoever. Increment simply increments. And it has void execute, bytecode interpreter, and string to string const. Oh, right, I have to tell the instruction what type of instruction it is. So type increment. Yeah, that's actually really cool. And then we will make decrement the same way. Decrement, decrement, and decrement. Cool. To string return increment. Oh, did I mess something up in the header? Yes, I did. Forgot to close that thing. Okay. And then how do we execute these? So increment execute and decrement execute. Let's worry about that in a moment. Let's just see how we would generate the code. So generator emit. So for incrementing, we increment like that. So I guess if op, no, what is it called? Op is the op increment. Else emit a decrement. And there are no other types. Yep. And then we need to store it back into the variable that we were reading from. So set variable identifier string. And yeah, so both set variable and get variable operate on the accumulator. So this actually, I think this lends itself to really nice code generation. So I'm happy about the accumulator architecture thing because it's so cool that you don't have to shuffle things around so much. Although I guess in order to support prefix versus postfix, we have to also, let's see. So the accumulator, by the way, is also the implicit return register, obviously. So like whatever the previous expression evaluated to should be in the accumulator when you exit the previous expression. So, or the previous instruction. So we need to make sure that the accumulator contains the sort of the result of the update expression, which in the case of a prefix increment or prefix decrement, we can just leave it as is because it will be the same as we just set the variable to. But in the postfix case, we need to remember what the accumulator contained before. So I guess if m prefixed, or no, if it's not prefixed, then we have to store away somewhere, I guess in a register. So like register postfix previous value for postfix reg generator, and then we will allocate a register for that, and we have to copy it there. So we have there's an op called store, which stores the accumulator content into a given register. So previous value for postfix reg. That register now contains the value before we perform the operation. And then afterwards, if it were not prefixed, then generator emit bytecode up load, and we will load back the previous value into the accumulator. Let's see, this feels reasonable. And then implementation wise, I think I'm gonna have to look at what we do today in the update expression execute. So update expression uses this abstraction we have in the AST interpreter called toReference, which sort of combines identifier and member expression types, both of those access types into a single thing called a reference. In our case, we have to generate pretty different bytecode depending on if it's an identifier access or if it's a property access on an object. So I'm not sure that the reference abstraction is like trivially transferable to the bytecode generator, but there are really only two types of reference. There's like identifier reference and member expression reference. So it's not a huge deal, I think. Anyway, maybe I'm wrong about that and we can create a good abstraction for it somehow. But either way, let's look at what this does. So when we execute an update expression, we get the old value from the reference and then call toNumeric on it. And if that throws, then we bail out. And then otherwise, if it's a number, we just add 1 to it. And if it's not a number, that means that it's a big int, I guess. So I think toNumeric is guaranteed to produce either a number or a big int. Yeah, so if it's a big int, then return big int, otherwise toNumber. So we know that will be a number or a big int. So let's see, what do we need to do? So this stuff we can kind of copy and bring with us. And we need to fetch out the old value first. So old value is, it's going to be the accumulator toNumeric. So we get the accumulator contents like this, and then we call toNumeric on it, pass in the global object, and then we have to check for exception. So if the VM has an exception, then just return. We still don't have exception handling in the Bytecode VM, but we just abort processing at that point. Let the main interpreter loop take care of it. And then instead of saying new value here, I think we can just do like interpreter accumulator directly assigned to that. Let's see, is this everything that we need to do? It's kind of neat. And in the decrement case, we just want to -1 or minus the big int with 1. Okay, let's try this. Am I missing something important? No, so it just does the update per spec and then puts the value back into the variable or into the reference. Okay, so it comes out the same way as with the AST interpreter, so I think it's correct. Let's also make a deck.js just for testing. So we'll go the other way around. It's a bit noisy like that. Yeah, it's identical. So if we look at, or let's make a simplified version. where we simply do ++I. So this has I assign 0 to I and then increment I. So what do we do here? We enter scope, we load 0 into the accumulator, assign a 0 to I, and then we get I and increment. We get I into the accumulator, increment the accumulator, and put the accumulator back into I. So very cute. These there's obviously like a bunch of redundant things happening, but I'm not sure that it's trivial to coalesce things with side effects being a thing. So I think perhaps with local variable access it's fine, but with something like member expression it's different. I'm not sure. Anyway, we're not going to get into that. Like, I definitely do not think that the bytecode engine is in any shape to be optimized at this point. We are still putting basic architecture into place. We're still implementing basic control flow and things like that. And I would ask people who are eager to participate in optimization work to hold your horses a little bit and wait until at least we can run our test suite correctly to completion before thinking about optimizing things, because it's just optimizing at this stage would just make it harder to work on it, I think. Anyway, just a note, because I know some people are eager to get into that. So I think this turned out pretty good. So let's do some commits here, or maybe just a single commit actually, because this UI here is a bit goofy. Can I don't know. It's weird that like I want the change list to be narrow, but I want the commit message editing pane to be wide enough to fit my 72 characters. So it's like I can't have both, which is a bit weird. Yeah, so just adding the increment decrement ops and adding cogen for update expression with identifier argument. Yeah, I think that's really straightforward and gets some good stuff done. So implement bytecode generation for update expression. We now added increment and decrement bytecode ops to support this. Prefix versus postfix is handled via or like let's say postfix update. Use a temporary register to preserve the original value. Yeah. Okay, wait, hold on. Note that this patch only implements identifier updates. Member expression updates still to do. Alright, to do. Yes. Okay. Yeah, let's commit that. So I think I just wanted to do a short video today to catch up, tell you what's been happening with the engine since I released the last videos, and do a little bit of programming so that we see that we're making progress. So I think I'll end the video here. So if you made it this far, then I thank you for watching and for hanging out. I really appreciate all of the great feedback that I've been getting on the series so far. And I'm super happy to hear that people enjoy it and that you learned something from it. And I will say yet again that I have never written a compiler before. I have no real experience with this type of stuff. So I'm most likely not doing everything correctly. So just keep that in mind. But I am definitely aiming to get better at this as I go. So I think we're doing okay. I hope you liked the video, and I will see you in the next one. Bye.